All right. Let's learn about binary trees. What up, Foxykins? Oh, I need my face. There we go. Let's do this. I need this to go away. I'm going to leave these open just because I might want to look at them later. And we're working on programming task 5 is our goal today. We are on lecture 7 out of 10, and lecture 8's less than half a lecture because we have the midterm. So we are cooking through this material like crazy. Programming task 5, we're going to use a binary search tree built using binary tree nodes, and we're going to use this to construct a playlist of songs, which is going to use our song comparators that we built in task 4. So we're going to start seeing a few different things come together here. We're also using linked lists, comparators, and then the new stuff, binary trees and BSTs. You won't use the BST class. We'll, of course, have the whole lecture to figure out what a BST is, binary search tree. But you will construct in the playlist class the concept of a BST. Just right off the bat, because I see that a lot. Students want to use the BST code, which you can use. Actually, what am I saying? I expect you to use it. I don't know what I'm saying. But what we want to do is create this playlist class where we can give it a comparator in the constructor. So we have our song title comparator and our song Bayesian average comparator. That's why we built these comparators. They use inheritance, so we built them in the inheritance homework, the inheritance task. But this is where we're going to use them in the binary tree task 5. So we're going to give one of those two comparators to the constructor, and nothing's stopping you from creating more, though I've never seen a student create a third one. But none stopping you if you want to. If there's a simpler one you want for testing, song title comparator is pretty straightforward, though, to sort just based on the titles. Give the constructor a comparator, add songs to your playlist, and then when you get song list, when you call get song list, it's actually this one. It's an overloaded method, so there's two of them. When you call get song list with no parameters, this is going to return all of the songs that you added to the playlist in the order according to the comparator that you gave the constructor. So that's what you're testing. Testing just the... that's testing utilities. Creating the playlist with a constructor and then calling get song list after adding songs. Those are the only things that you're actually get song tree as well. That's the main functionality that you're testing is, will this playlist order my songs based on my comparator? Morning to Tatia. Will this playlist order the songs based on the comparator that I gave it? So if you actually have a playlist of songs, you're adding songs, and you want them to come out in alphabetical order, or you want them to come out in Bayesian average order, all those songs, your song list, when you actually play the playlist, should come out in that order, whatever order you gave it. So that's the goal here. And then the testing utility method is comparing two song trees. So you have two trees of songs given by their root node, and you have to traverse both trees and make sure they have all the same values at every single node. So this is your comparing two linked lists objective, but amped up to binary trees. So I'm looking forward to, I'll say, all of the null pointer exceptions that we're going to see. Most of you are past task 3 at this point, so hopefully there's not many more task 3 null pointer exceptions to see. As much as I harp about it in lecture, there's still so many Piazza posts and so many office hour questions that all start with task 3 null pointer exception. So same thing here with task 5 null pointer exceptions. Always assert that a node is not null. Do not assume that a node is not null. And where that comes up, actually I can't even say most this semester, but where it usually comes up the most semesters, is in your testing. When you test the get song tree method, the intent here is you call create a playlist, add a bunch of songs, call get song tree, create the song tree that you expect, and then send it to your testing utility method. I might give a demo. I don't know where I'll find. I probably won't because I won't ever find time to do it. But so I'll just give a blurb right here. Is you should be calling your testing utility methods in your testing requirements. That's the whole setup. That's the whole point of the testing utility methods. That it's a utility that you get to use to help you write your test cases. And I'm seeing a lot of questions, a lot of office hours and Piazza questions that wouldn't exist if you just called your testing utility methods. And this is one of those tough things because anyone who's hearing my voice probably didn't have this issue. I'll venture a guess. I'll be so bold as to assume that it's the students who don't watch lecture. It's the students who watch lecture at 2 times speed and don't comprehend a word I'm saying because they just want to rush through it real quick and then waste their time by not understanding how to do the homework for hours and hours on end, or maybe it's more innocent and they just forgot. But call your testing utility methods, please. If you're somehow hearing my voice and haven't been calling your testing utility methods, call your testing utility methods. And the idea here is that you'll create your expected value. So what you expect based on the comparator and the songs that you added to the playlist, there's a certain song tree that you're expecting. So call get song tree on your playlist. That's going to return a tree. It's going to have all those nodes in a very specific order and very specific places based on inserting into a BST. Create a tree with that expected order, that expected tree, with all of the values that you expect for all the songs, all the ratings of those songs, all the titles, artist IDs, everything exactly the way you expect. And then call your testing utility method that will compare your expected tree versus the tree that came out of the get song tree method. If you're doing that for all of your homeworks, you'll never see issues in your testing I had to spend a lot of my time answering questions on. Just call your utility method. Like the whole homework is structured. Write your utility method, use your utility method, and then use your tests to finally implement the code. That's been the structure since day one. Well, I can't say day one because task one didn't have a testing utility method. Maybe I should add one just to drive this point home right off task one. But why is this still counting up? Bugs me. So call your testing utility method, especially on task 3. It would have prevented most of the null point. I can't say most this semester, but it would have prevented a lot of the null pointer exceptions, especially in the tests. I wouldn't have to say, well, when I'm testing for feature coverage in your tests, I'm actually testing your tests against my incorrect solutions and making sure your tests get my incorrect solutions marked as incorrect. And those incorrect solutions sometimes return null when you don't expect it. So you have to assert that the node is not null before you use the dot operator on it, which is true throughout your career. You should always be asserting things to be not null when they come from an untrusted source. Don't just make assumptions about what that untrusted source gives you, whether it be a third-party library, a Java library, your colleague's code. Don't just assume that it's not going to give you null, especially when it's a data structure that uses null as part of its functionality, because at that point you're assuming the size of the linked list. If you say node equals, get the node from the song, the node for the head node for the list of ratings in task 3, and you say assert that node dot get next dot get next dot get value dot get rating equal 5, you're assuming that you got a linked list of size 3 without asserting that. So that's where a lot of those null pointer exceptions come from. So just a heads up on that whole conversation will apply here as well, except with trees instead of linked list. So and also with linked list, with the get song list, this will be a linked list. So null pointer exceptions aplenty, a lot of landmines to avoid. Just make sure you're always asserting that your nodes are not null. Don't assume that they're not null. Would it be more helpful for me to go through both trees at once, or could I just convert each tree into strings and compare the strings? I'll say whatever works for you. If you can convert to strings and that works for you, I'm not going to stop you, but that sounds like it'll have more issues. more issues than it'll help. Because this is a binary tree of songs, first of all. So you'll have to write a two. No, that's not even going to work for you. Maybe. But your two-string method, you would have to write in test data structures to, or somewhere in your tests package, because you'd be tempted to give song a two-string, and song has a linked list and ratings, so you have to give linked list and ratings, those classes, two-string methods. But then when you submit to Autolab, my correct solution won't have two-string methods for any of those classes. So you can't put them in the classes, but if you want to write another helper method that converts a binary tree into a string, but I foresee issues with that. You could have two different trees that resolve to the same string if you're not careful. I think that'd be too tricky. The intent is to traverse both trees at once, which I'll say this compare song trees. The intent of this one is to give you practice with recursion. I'll just come right out and say what this one's assessing. This is intended to give you practice with recursion, and if you use recursion, this method isn't that bad at all. You already have a method that compares two songs, and you have a method that compares two linked lists of ratings. So you'll want to combine those two, even if you add the linked list of ratings to your song compare songs method. But somehow, like, you already have the code to do all of that stuff. Once you have two nodes that you're comparing the values of, you already wrote all the utility methods to be able to compare those two songs. Even if you do compare songs and then compare song.getRatings, compare song.getRatings, and compare the linked list of ratings, you have all the functionality to do that. That is, I'm second guessing myself, but that is the utility method here, right? Yeah, test list, compare lists of ratings. So you already have compare lists of ratings and compare songs. So reuse those utility methods. This conversation spans across tasks as well. Previous utility methods that you've already written, use them. Like, use them. Please use them. And that's my hint right here, that you can use those older ones. You do have to create instances of your test classes, which is a little awkward, I have to admit, because we made those non-static. So you have to create instances of them, but it's not that big of a deal. We got that. So you have those utility methods, call them. This is one of the biggest things that I see students missing is it first comes up in, I'll try to cut this, I'll try not spend too much time on all this, but I want to give homework hints because there's so many little things that I constantly see students falling into, and even after this, they'll still fall into it because I think what students do is skip my intros all the time, and once they see a slide on the video, they'll go to that slide and then watch it 2 or 3 times speed. It's not the way to study. Like, this is where I'm giving hints for the homework. But I saw it a lot with compare ratings and compare reviewers. When it was into the testing requirements on test 2, instead of calling the utility methods, they'll say like rating.getRating equals rating2.getRating, and recreate all that work in the testing requirements. And inevitably, or I shouldn't say inevitably, but the ones that come to me anyway, the ones that make it to Piazza and office hours, are the ones who forget to check something. So they check the rating, but they don't check the reviewer ID of a rating. A very common issue to have in this one. They never check the reviewer ID because they're testing the reviewer.rateSong method, and they'll check the reviewer's reviewer ID. They'll check the ratings rating, but they won't check the ratings reviewer ID to make sure that rating got the right reviewer ID for that reviewer. But if you're using your utility method, you cannot make that mistake because these methods are tested by Autolab. They're proven to be correct. I shouldn't say proven, but they're most likely correct on all cases. There's some times where you can have a very obscure bug that I didn't test for. It's very rare, but I feel like that came up once. Over the course of years and thousands of students once. But if you call these methods, you will never have that issue. You don't have to remember. And that's what we like as programmers. We don't want to have to remember stuff. Like, ever. I don't want to remember anything. I'm going to write these methods once. I'm going to write a compare ratings method once. Or I'll use compare songs because that's more relevant to test 5. We write compare songs once, and we just call compare songs. Now, compare songs doesn't compare the ratings, so you have to keep that in mind. That you do have to call the ratings, because when we wrote compare songs, songs didn't have ratings yet. So we do have to compare the ratings as well. But I want to write that once to check artist title ID. One time I want to write that. And then I'm going to use that utility method throughout all 8 tasks. Whenever I have to compare 2 songs, I'm just calling compare songs. I would even add a call to compare ratings in compare songs, so I don't have to make 2 separate calls anymore. But that's my advice for the day on that one. That's task 5. Let's learn how to do it. I'm going to download all the slides so I don't have to go back to this. I'm excited for the timing of today's lectures. Usually I have to rush Monday and Wednesday, and then Friday is too lax. So I have time for this 15-minute intro. I usually don't introduce the homeworks in fall and spring. I want to introduce each one over the summer. So I have time to do that and get all the material in at the pace that I want. I think today's going to be a lot better as a 2.5 hour lecture than as a week, because the lines between the lectures, it's the week is very clearly 2 topics, so it makes sense to have them in 2 days, and I just can't really do that in a fall or spring. Okay, so let's get into it. What is a binary tree? And the definition is super simple to understand, given that you understand linked lists. It's just like a linked list, except it has references to 2 nodes instead of just 1. And that's the difference. That's it. You now understand binary trees. So a linked list has just a reference to the next node in the list, and we have these nodes. Each node has a value and a reference to the next node in the list, and we can go next, 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 next to traverse the list until we see null. That means we've reached the end of the list. With a tree, it's similar, except each node has a value and 2 references, which we call a left and right reference. So we have 2 references to 2 different nodes instead of just the next node. There's the left node and the right node, and we call these child nodes, and the node itself is the parent of those child nodes. And yes, the whole family tree analogy applies here. We're only going to see just child node. I don't even think I used the word parent node outside of this slide. But the term child node is the one that we're going to use the most, or exclusively from this analogy. But the analogy does extend, so if you do study trees, you will, in 250 and 331 at the very least. And if you go further into trees, the whole analogy applies, so you have grandparent nodes, grandchild nodes, ancestor nodes, descendant nodes, aunt and uncle nodes. I've only heard one time there was a problem that needed to know that relationship between nodes. The siblings, children, but the whole analogy extends. Child nodes is the biggest thing that we're going to need to know. Visually, this is what it looks like. This is how we'll draw our trees. Where linked lists, we like to draw them from left to right for no real reason, just because that's the way we read in the United States, I suppose. I never really thought of it, but this is how we do our trees, which is upside down from a natural tree. By the way, there's a second analogy that runs through trees, the natural tree, and from nature, where we have roots, branches, leaves, all that good stuff. But the root is on top. We do them upside down because that's how we do things. We like to do some things backwards. So the root node, like we had a reference to the head node of a linked list. When we have a binary tree in our program, it's just a reference to the root node, which is the first node of the tree. And then that node can have right and or left children. Those nodes can have right and or left children. And then these, what we call the leave nodes, I won't harp on this analogy too much except for the word root. I'll say the word root node all the time. But these leave nodes that don't have any descendants, any children, have null references. So if there is no left node, it has a reference null reference, no right node, null reference. So null is still being used to indicate that we've reached the bottom of a branch of the tree, but there's not just one null. We have to have nulls for every the end of every single branch in the tree. And this is what we call a balanced binary tree, meaning that it's nice and symmetrical. Each descendant has the same number of descendants. The left and right trees have the same number of nodes in each of them. And I like this one just because it's pretty on a slide. That's the only reason I use this tree as the example, and I'll use this one throughout this whole lecture. I use it throughout the whole week in the fall and spring. We'll use it all day. But the tree doesn't have to look like this. So don't fall in the trap of thinking that just because I'm using that one as the lecture example, that the left and right nodes are either both references to nodes or both null. We can have all four cases here. We can have left and right both being null. We can have left as null, but right is a reference to a node. We can have left as a reference to a node and right is null. Or, as on the previous slide, we can have right and left both have references to nodes. All four cases are valid. So in your code, you need to account for all four cases. For example, I'll sometimes see students write code if left is not null, then they'll just assume that left and right both are not null, and they'll get a null pointer exception when they try to go to the right because right was null. You need to say if left is not null, you can go over here. If right is not null, we can go over here. You have to check both nodes for null, both child nodes for null. So 2 null checks here for each node in a tree. Don't forget them. I don't want to see any null pointer exceptions. I want to. It's one of the things like, what do I have to say to get everybody to avoid null pointer exceptions? Because it can be a frustrating error. Because every time it's a null pointer exception, it's, well, I don't get a null pointer exception in IntelliJ. I only get it when I submit to AutoLab. So it can be a frustrating one to find out. It's one that you, dare I say, actually have to understand. Can I be that bold? You actually have to understand this because it's not something that the IDE is just going to yell at you and say, hey, you're going to have a null pointer exception here. It's going to silently let you make that mistake. And then when I run my tests in AutoLab, I'm going to find that mistake. IDEs are nice tools, but they're not always going to help you. Not always going to do what you want it to do. There's certain issues that you just got to actually know how stuff works. Hey, I don't want to go on this tangent. I don't want to go on that rant, but there are certain tools you can use that, can help, but if you're too reliant on the tools, you're going to eventually have a really, really bad time. Really bad time. IDEs are pretty fine these days, but once you turn on like AI assistance on the IDEs, you're just asking for huge trouble. Or if you're going beyond that, like some students do, it's going to be a huge wake-up call at some point in your, I would say career, but your career is not really going to exist, unfortunately. That's the harsh reality of it, unfortunately. I accidentally went down this rant a little bit, so let me clarify. It's when you're using AI to cheat. Like, if you're not using AI to cheat, don't worry about what I'm saying right now. But too many students use it to cheat and have the AI do the homework for them. And it's a tough one because they won't have careers. Like, I'm here to help you start your careers. And some students will just say, no, I don't want a career. And they'll use tools like that. I don't have a good solution for it. For the time being, I have to just kind of sit back and watch them, waste 4 years of their life and a bunch of money. It sucks. I hate it. So here's the binary tree node class that we use. And unlike linked list node, like we wrote a bunch of methods inside the linked list node class. We're not going to add too many methods to this binary tree node class. I think it's exclusively the getters and setters. In the repo, I think there's also a toString is the only other method that we add to this class itself. But I'm not even going to add the toString in the slides. Actually, I think I do show it a little bit, but we don't need to add any extra methods to this class itself. This is the whole structure of a binary tree node, and that's it. We're going to leave it at that. The methods that we're going to write to work with binary trees are going to be outside of the binary tree node class. They'll be in separate classes. So this is it. As promised, we have a value and then references to two other binary tree nodes. We have a type parameter, so we can have binary trees of any type. And the references to the other nodes are labeled left and right, and then a constructor to set those three values. Pretty much like a linked list, we just have two references instead of one. So the structure is very similar, especially in the code, very similar to a linked list. It's the implications of that structure. That's what we have to spend the rest of the lecture on, most of the lecture. The structure isn't too hard to understand. Like, you should all be able to understand what's on the screen right now. But what do we do once we have our hands on a tree? That's the big thing that we're building up to. Like, what do we do with that? Spoilers, the answer is going to be recursion. Lots of recursion. So we're going to create a new binary tree node, and I'm actually going to create this manually. We're not going to ever have an append or prepend or insert method or add for the binary tree node class. We will in the BST class that we're going to do after we understand what trees are. We will in that class, but in this class we're not going to add anything in the binary tree node class. So we're going to build our trees manually, and this is the way it'll be on the midterms, the way it is on the sample midterm. Oh, I meant to announce that. If you don't check Piazza regularly, I posted a sample midterm. Later tonight, I'll post the solutions to the quizzes. Not sample midterm, but 2 sample quizzes, and those quizzes are meant to look very, very similar to what you'll see on the midterm. The 4 quizzes on the midterm, you're going to open the midterm, and you're going to look at 2 quizzes that are very similar to the OOP sample quiz and 2 quizzes that are very similar to the data structure sample quiz, to the point where you're going to look at them and be like, wow, he barely changed anything. That's intentional. I want you to understand how to trace code like that. I don't care, if you can do it once, you can do it 100 times. Make sure, like, the sample quiz has all of the learning objectives being assessed. Like, all the learning objectives I need you to understand are in that sample quiz. So if you study that and understand all those things, and then show me on the midterm that you can do that with a new, similar, but different enough that you can't just memorize the sample, then we're good. Like, that's all I need from you. That's what I need. So study those sample quizzes. I'll get the solutions out tonight. I wanted the quizzes themselves out long enough that you're not tempted to look at the solutions that are right there, that you can work them out on your own, and then I'll release the solutions so you can see those tonight. So we're going to create our tree manually. That's how I got on that segue, which is very similar to how we're going to do it in the quizzes. This one's a little bit different because this is in a main method that's in the binary tree node class, even though it doesn't look like it on the slide. That's why I'm getting away with dot left and dot right, but these will have to be dot get right, dot set left, dot getters and setters here. And on the quiz, I created my nodes, instead of putting all nulls here, I just put my nodes right in the constructor calls. But if we're tracing this code, we should be able to follow what's happening. We're creating a new binary tree node. Looking at this slide, it's probably a little fuzzy what's happening. Maybe it's clear. I don't know. But if you went through and traced this, like, there's no new concept here in terms of tracing. It's a constructor call a whole bunch of times. It's a whole bunch of constructor calls. So pass the arguments where they go and return the values where they're being assigned, and you would be able to trace this code. And you'd see the structure of the tree pan out as you do that. But let's walk through it just to be sure. We're creating a new binary tree node with the value 5 and no child nodes, and assigning that to the root. And unlike our linked list where we kept reassigning our head node, we're actually going to keep the root as a reference to this node. The root will always have the value 5 in this example. And then we're going to say root.left equals a new node with the value 2 and null null. So at this point, we have the root node with the value 5, and then its left child we're assigning to a new node with the value 2, and its right child is still null. So we effectively replace this null, the left null, with a new binary tree node. We're going to replace its right node with a new node with the value 8, and then we're going to set its left, the root's left node to the value -3. So we're starting at the root. We're going to its left node, which is now this binary tree node right here, and setting its left to a new binary tree node with the value -3. So the root's left is this node, and this node's left is this node with -3. We're going to set the root's right node to the value 4. The root's right, which is this node, is left, so we're replacing this null with a node with the value 7, and then its right with a node with the value 14. So we're manually building this tree by setting the left and right nodes to null in the constructors, and then replacing them as we add more nodes to the tree. So a different way of setting things up, but we get the same effect here as any other way of building the tree. Like on the sample quiz, honestly, the sample quiz is probably going to be more like what you'll see on the midterm as well, just because this should be getters and setters. Like this line should be root.getRight.setRight of new binary tree node, which is a lot of getter and setter calls, which is just tedious and annoying when you're tracing it. And I don't want to do this .right. I don't like, I should really update this slide because I don't like this at all. And it's .right, .left. We're accessing private instance variables directly. We can do that because this main method is inside the binary tree node, but I still don't really like it. Just because we can doesn't mean we should do that. But it did make that code a lot easier to write for what it's worth, which is a horrible reason to do that. So finally, let's get on to the big question we want to ask. How do we do anything with these trees? Like with linked lists, we went through the linked list until we saw null and processed each node as we visited the node. So if we're printing them to the screen, if we're taking the average of the values of linked lists, whatever we were doing, we process a node and then we would make a recursive call to the next node until we see null. So how do we do this with trees? What do we have to change and expand when we start doing this with trees? Well, we have 2 nodes now. We're going to make 2 recursive calls. What more do you want from me? That's what we're going to do. 2 recursive calls. So we're just going to make recursive calls on both child nodes. That's the difference. Not much of a difference here. Not much of a difference. And we're going to see 3 ways of traversing a tree. All 3 of these ways are different orders in visiting the nodes. So, for our purposes, visiting a node, we're going to do the simplest things. We're going to concatenate strings. We're going to write a toString method in class. But there's 3 different ways to do this: pre-order, in-order, and post-order, which is going to affect the order in which we visit the nodes. So here's in-order traversal. What in-order traversal means is that we're going to make a left recursive call. Then we're going to visit the node that we're building, and this is a toString method, so we're going to call toString on the left. Well, it's not toString itself, it's an in-order traversal, but it's returning a string, so it's effectively toString. We're going to make the recursive call on the left. That should return a string for the entire left subtree. I didn't introduce the term subtree. I do like the subtree term. This is going to the left child and treating the left child as though it were the root of its own tree. That's what I call the left subtree. So this converts the whole left subtree into a string. Then we're going to concatenate to that the value at this node, and then concatenate to that the value of the right subtree as a string through this recursive call, and then return that big concatenation. And if the node itself is null, I'm going to return the empty string. So this, again, is a recursive method where I will call it with node as an input. There's, getting a little ahead of myself, but I want to make sure I say this. There's two different main strategies with recursive calls like this. One, and we did this with linked list too, but I want to remind you because it's going to come up, is either we just make the recursive calls with no null check. That's what I'm doing in this case. I just make the recursive calls. I did not check if left was null or not. So I'm apparently risking a null pointer exception. The thing that I have to keep in mind is that this method can get null as an input. So I have to check for null before I use the dot operator. If I say no dot is the first line of this method, I will get null pointer exceptions 100% of the time. Because we're eventually going to reach the bottom of a branch, and it'll be a null pointer exception. So I have to check for null at some point, and I decided to do it at the beginning of the method, and I'll call the method, make recursive calls with null as an input. The other approach to this is not making the recursive call if the value is null. So the other way is saying if node.left not equal null, then make the recursive call. And then I wouldn't have the null check at the beginning of my method because I have it. I'm checking before I call the method. I'm always checking for null. For what it's worth, I like checking for null in the method and calling it with null. In this case, it's a little less code. I'd have to have 2 null checks if I checked before making the recursive call. But here I only have to have 1. On the sample quiz, I do the other approach. So I want to make sure I give you examples of both. So no matter which one I throw at you on the midterm, you're going to be prepared for that. On the midterm, I do check for null twice. I check the left for null, and then if it's not null, I make the recursive call. I check the right for null. If it's not null, I make the recursive call. So 2 different strategies. The one on the sample quiz has fewer stacked frames, is the big thing. So it's less tedious to do that on an exam. You'll probably see that one on the midterm. But in lecture, you're going to see a whole bunch of stack frames where the input is null, and it does get a little tedious. I made the slide, but do I want to make all of you do that? Probably not. So in-order traversal is where we're visiting the node in between the 2 recursive calls. So there's 3 different choices of when to visit the node in question. When we visit a node, when do we call it? Do we call it in between the 2 recursive calls? Do we call it before the 2 recursive calls? If we call it before, that's our pre-order traversal. Or do we call it after? If we visit the node after, that's our post-order traversal. So that's our 3 traversals is when do we visit the node? Before the 2 recursive calls, pre-order, after both recursive calls, post-order, or in between the 2 recursive calls, which is in order. So all 3 are almost identical code, and they are pretty much identical logic, identical concepts and ideas. It's just a question of when we visit the node in relation to the recursive calls. And each one of those is going to give us a different order of visiting the nodes. And here's the code for all 3 traversals. You want to visit every node in a tree, and what all 3 of these traversals will do is visit each node in the tree exactly once, which is often what we want. When we're traversing a data structure, we want to visit every single node exactly once. So you can imagine if this is finding the minimum value of a binary tree node of integers, whatever we're doing with these. Yeah, these traversals are in the binary tree node class. I want to get those out of there. They shouldn't really be in there. That's why we get away with dot left and dot right and dot value. And I don't like them in there. Don't like them in there. So these are effectively 2-string methods, but we can't call them 2-string because there's 3 of them. We can't have 3 2-string methods. So this is the code for all of them. Not a lot of code. And here's where I'm going to give my big, not long, but my important point of how powerful recursion is. So with linked lists, I gave you, every example I gave in lecture was recursive. And I said, get practice with recursion, but loops are pretty much the same difficulty. It's about the same amount of code, except you don't have to understand recursion. But I strongly recommend that for task 3, you use recursion for all your methods to get practice with recursion. Binary trees is why you want that practice. Because these methods don't get much more complex from compared to the linked list methods. Anything I asked you to do with the binary tree isn't much more complex than what I asked you to do with the linked list if you're using recursion. So those of you who decided to ignore my callings, and yeah, that's fine. I get it. Like task 3, if you're facing a deadline, you just need to get it done. You're gonna pull out what you know, which is loops. Like I understand why. That's fine. But I am saying this is where it catches up to you. It catches up pretty quick. Just a few lectures later in the summer, it catches up to you because you're gonna want recursion here. Try, and if you don't believe me, just try to write one of these traversal methods without recursion. This is where I can no longer say, loops are pretty much the same. Like it's the same stuff. No, recursion significantly more powerful here when we're traversing trees. This is where if you're not using recursion to traverse trees, good luck. It is possible. I have had students take me up on this challenge, so I'll challenge you, if you are a non-believer of recursion, try to write one of these methods without recursion. It is doable. I have seen, I think I'm up to like 5 now, like 5 students over years. That's out of thousands. I think 5 students have taken me up on this challenge and have done it. And every single time, the code is way more complicated and way more involved than these methods. Like a lot of this is just overhead, creating the initial string and then a couple of return values. I can do this in 5 lines of code without the overhead. If I'm, say, just printing to the screen, I check for null, I make the left recursive call, I print to the screen, I make the right recursive call, and I'm done, and I'm out of there. I guess that's 4 lines of code to visit every single node, and the rest of it is to handle what we're actually doing is converting this value to a string. Just try to print every node's value to the screen in a particular order, visiting every node exactly once without using recursion. It's possible, but it is significantly more work. It's significantly more complex. But going from linked lists to trees, if you already have the practice with recursion, you basically just slap another recursive call on there and call it a day. You're going to want to use recursion here. So if you didn't use recursion for linked lists, this is going to be difficult because your first recursive methods you write are going to have 2 recursive calls, which increases the complexity significantly. But that's the hole you dig yourselves if you don't practice recursion. This is where it catches up. On the plus side, when you're done with task 5, you will have some recursion practice because it's the easiest way out. The easiest way out of task 5 is actually using recursion. You're not going to want to use a loop here. So, end of that discussion. If you don't believe me on any of that, you'll believe me by the end of task 5. You'll want recursion. If you don't use recursion for task 5 and you're like, screw this, I'm not learning recursion, let me know because I'd like to see your solution. I'd like to see what you come up with. With task 5, the crux of task 5, the bulk of the difficulty is taking a tree of songs and traversing the tree while converting it into a linked list of songs using an in-order traversal. So you want to traverse, make a recursive call, this will give you a linked list, recursive call, this will give you a linked list, and then get this node's value right in the middle of both of those linked lists and return ahead to the completed linked list that you're constructing. Doing that without recursion would be a nightmare. I don't want to do it. That'd be maybe I'll do it some days, just an exercise in frustration, but I don't want to. I don't even want to think about doing that. It's way too much work. Certainly way more work than I would expect any CSE116 student to ever do. Like, I wouldn't say you have to traverse a tree without recursion in order to pass this class. That'd be ridiculous. That'd be way too outrageous of expectations. And students say the expectations of 116 are already outrageous, so I definitely would not do that. Use recursion. Love recursion. Recursion's great. Okay, so in 3 slides, I want to just show the difference in the orders of these traversals. With an in-order traversal, we're making the recursive calls and then visiting a node. So the way that works is we'll start at the root, make the left recursive call, left recursive call, left recursive call, and I'm shortcutting my nulls here. This is null. This is null, so it returns empty string. And then we visit this node because we've already made its left recursive call, but we haven't made its right recursive call yet. So -3 is the first value in this string. Then we make its right recursive call. That's null, so it returns. This stack frame here was waiting for its left recursive call to return, which it just did. So it was on this line. Now it's moving on to the next line, visiting this node, get 2. Then make its right recursive call, left recursive call, visit the node. So 4, right recursive call, return, visit 5. Right recursive call, left recursive call, left recursive call, return, visit 7. Right recursive call, return, visit 8. Right recursive call, left recursive call, return, visit 14. Right recursive call, return, and we return that string back to the caller. We do have a memory diagram at the end of this lecture, so if that was way too fast, and the next 2 will be just as even faster. If that was too fast to follow, don't worry, we will break this whole thing down in a big old memory diagram that's going to take like 20 slides. But that I just want to do the comparison of the orders. This is going to visit each node in order. In order doesn't make sense to us right now, but when we get to binary search trees, that'll make a little more sense. It'll actually have some meaning for us. Pre-order, we're going to visit the node and then make the recursive calls. So in pre-order, we visit the node first. So 5 is going to be the very first thing. The root's always going to be the first value in a pre-order. Then make the left recursive call, visit 2. Left recursive call, visit -3. Left recursive call is null, return, visit 4. Call, return. Right recursive call, visit 8. Left recursive call, visit 7. Return. Call recursive call on the right, visit 14. Recursive call, return, and return back up to whoever called this method, whoever was interested in traversing this tree. Post order, the root's always going to be last. In a post order, we're going to make a recursive call, return, recursive call on the right, return, and then finally visit our first node of -3, return, right recursive call, left recursive call, return, right recursive call, return, visit 4, return, visit 2, return, right recursive call, left recursive call, right recursive call, visit 7, return, right recursive call, visit 14, return, visit 8, return, visit 5. So those are our 3 different orders. The most important one to us in 116 is going to be in order. It's the one we're going to actually extract some use out of. Pre-order and post-order, we're just not going to see any applications where that's going to be critical. There are applications out there. I used to do examples using expression trees where each node is either an operator, like and I use the four operators, plus, minus, subtract, addition, subtraction, multiplication, division, or an operand. So every node either had 2 children or 0, and if it had 2 children, it'd be an operator. If it had no children, it'd be an operand, and then we could use that expression tree to represent any algebra that we wanted, any equations that we wanted. And then pre-order and post-order would give us different ways of representing those equations using prefix and postfix notation or infix notation, which is how we're used to reading them. And it was just too much. I'm like, I spent so much time with that, and I had so many slides just to give an example of pre-order and post-order, and it wasn't worth it. So we have no applications of this. Just know that in the future, you might see applications of pre and post, because visiting the nodes in these orders do have applications, and you might come into them in your career. Hopefully they have examples in 250 and 331 of when those two are useful. We're only going to get use out of in order, but on your midterm, I might throw in order, post order, pre-order. Whatever one I throw at you, make sure you're actually following the code, and whatever the code tells you to do, just make the recursive calls in that order. If you're blindly following the code, you shouldn't even have to know that those three orderings have different names. You'll just trace the code and follow the code in the order that it's telling you to go in. But I'll throw one of those three. That's usually how I catch students. Not catch, but some students will overstudy for this one. This is probably the quiz. Whenever there's trees on a quiz, which there will be on all your data structures quizzes, whenever there's trees on the quiz, students will overstudy the lecture example, and whatever traversal I use in lecture example, so I'm using a post order here, whatever traversal I use in lecture example, they'll just do that. They won't read the code that's given on the quiz. They'll memorize the lecture example and then regurgitate that lecture example on the quiz. Also, the lecture example is going to make a whole bunch of calls to null. We're going to see stack frame for a traversal node is null, and it just immediately returns. We're going to see a lot of that as well. And if I don't have that style, I'll just say it right out. Like, I'm not going to do that on the quiz. The quiz is going to have your null checks before making the recursive calls, just so we don't have all those extra stack frames. And it's at a glance, I'll pull up a quiz submission, and if I see all those nulls, and especially if it's the wrong traversal, if it's a post order because that's what I did in lecture, and there's a bunch of null checks because that's what I did in lecture, I know that's a student who overstudied, tried to memorize, which, by the way, in computer science, we don't want you to memorize anything. I feel like I just said this at the top of lecture too. I don't want to memorize anything. I don't want you to memorize anything. I want you to understand concepts and be able to apply those concepts to new novel problems that you see. Because that's exactly what you'll be hired to do. You're not going to be hired to regurgitate my lecture example. Like, nobody gives a shit out there in industry. Like, can you show me what your professor showed you in class? Like, verbatim? Nobody is going to pay you 6 figures to do that. Nobody. They want you to solve their problems. I need to prepare you to solve their problems, and I don't know what their problems are. And even if I did, there'd be like a million of them. I can't prepare all of you for all of the problems that you're all going to see in all of your careers. It's not practical. You need to understand the concepts and apply them to new things. So it's always sad when I have to fail those students. Like, I studied your lecture slides exactly, and I have to explain to them, like, it's not what I need you to do. It's just not what I need you to do. Okay, so we're going to start with the main method. And I'm going to have a visual of the tree that I'm creating. And I do recommend this, like when you're doing your quiz, even if you have a scrap piece of paper and you sketch out your trees for your data structure quizzes, it can help just to keep track of everything. But it's not required. You can't do this on the tracing tool at all. Your tracing tool, it'll be the references and following the references. But I'm going to visualize it over here just so we can keep track of everything in a better way visually. And I am cutting down the code a few little things I have to mention for the slides. BT node instead of binary tree node, but it's the same class that we saw before. I cut out all the code here, but it's the constructor, and I do have I didn't. Don't use getters and setters here either. I should add my getters and setters, but it is more tedious to do that. So both these methods are inside the BT node class. That's why I'm able to access the instance variables directly, even though they're private. Okay, BT node constructor. We've seen 100 constructor calls by now. We're good with this. This one doesn't even have inheritance, so I don't even have to worry about super constructor calls. BT node. This is a reference to the object being created. Label the type of the object. This constructor happens to take all 3 instance variables. So I have all 3 instance variables here, all 3 constructor parameters here, and this a reference to the node the object that's being created. That returns over to the root variable in the main stack frame, and we move on to the next one. We're going to say root.left. So this stack frame, and this is something I know you can't do in the tracing tool, so I wouldn't put this on a quiz exactly this way. But this constructor call is going to return to an instance variable on the heap. So I'm going to put my arrow pointing to where it's returning. It's returning to root.left. That's where it's returning. So we have another constructor call. We replace that null with OX200. Then root.right. Root.right equals, so this is where we're returning the value. A new binary tree node, create another binary tree node. Its left and right are null, 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 null for all these ones. Then root.right.left. Root.right.left equals, so this is where we're returning. And it equals another new binary tree node. So another constructor call, another object created. This is a reference to the object being created. Nothing new there. So let's get to the new stuff. Or I shouldn't say nothing new. The new thing was returning to instance variables on the heap, which is, I don't really have anything to say to that. It's something we can do because, I don't know, of course that's something we can do. We've messed with instance variables on the heap quite a bit so far this semester. Here we're assigning them directly, but only because this code is inside the BT node class and I can access the instance variables directly, but usually it's not something we want to do. I mean, we did it with linked lists a lot too, so I guess that's not even anything really that new, but not exactly in this way. Anyway, let's get to the good stuff. Let's get to this traversal. So we're going to call traversal on root, and this is a static method. So every once in a while we do sprinkle in a static method here and there. It's static, so there's no this in this method call. So it's traversal, and it's just going to have the node that it's being called on, and that node is root OX350. So node gets the value OX350, gets the value of the root variable, which is not a binary tree node object. It is just the reference. Again, that's review. And then we call traversal with OX350 as node. If node not equal to null, that is true. Node is not equal to null. It's equal to a reference to a binary tree node, OX350. So since the node is not null, we're going to make both recursive calls and then print this node's value to the screen. And we're going to have a lot of calls on the stack when we do this. We're going to have a lot of frames on the stack at the same time. So I'm going to color code my stack frames. And the big thing that we're going to watch as we go through this traversal is where each stack frame is in its execution. So we're going to have this stack frame right here, which is going to make a recursive call on its left node. So we're going to call traversal on node.left. Node.left is OX200. So node is OX200 in the next stack frame. But we have to remember that this stack frame is sitting right here on this call. It's waiting for its left recursive call to resolve before it can gain control again. So we have to remember where this node was, or where this stack frame was in its execution. So we're going to make this recursive call on OX200. It's going to do the same thing. Node is not null, so make the left recursive call. So node is not null, make the left recursive call. Node.left is null. So we're going to make a recursive call where node equals null. Since node is not null is false, because node is null, we skip the conditional code. We skip this code block. This is our base case. This is a call to our recursive method that does not add any new recursive calls to the stack, which we have to reach these base cases if our recursion's going to end. If you don't reach a base case, you go infinite and you get timed out after 180 seconds in Autolab. That's always going to be because you went infinite in CSE116 anyway. There was one case where I had students that just had such inefficient code that it was timing out because of that. I got rid of those test cases that were causing that issue, so now I can confidently say, unless you intentionally write really, really, really inefficient code, your timeout's always going to be going infinite. Okay, so this call of null, node is null, doesn't do anything. It's just going to return. And we're returning to the next frame on top of the stack. So we pop this stack frame off of the stack. This is now the top of the stack again, so this is the active stack frame. When we get back to this stack frame, we have to remember where we were. So this stack frame was waiting for its left recursive call. So now that left recursive call just resolved. This returns void, so it didn't return anything. But this resolved. So now we pick up execution at the next line. We go to the next line and make the right recursive call. So we're going to make the right recursive call because that's where we're at. That's where we're at in the execution of this program. Now we make the right recursive call, and still, again, we're going to remember that we're at the right recursive call. So this stack frame is making its right recursive call right now. Make the right recursive call, that's also null, node.write. That's also null. So that just returns and does nothing. Now we're back at this stack frame again, and we're remembering that we made the right recursive call and we were waiting for this recursive call to resolve. Now that we're back at this stack frame again, we can pick up execution after that recursive call, and finally we're able to do some real work. We're going to print to the screen this nodes.value of have. So we finally get to print something to the screen. It's a post-order traversal, so we got to make both recursive calls before we can visit the node's value. And then that stack frame's done. We hit the end of the method. This stack frame returns, pops off of the stack, and now this stack frame is the active stack frame again, which has a reference to what we think of as the root of the tree, OX350. It was waiting for its left recursive call to resolve, which it just did. So now it's ready to make its right recursive call. It makes its right recursive call node.write OX480, which also makes its left recursive call .left, which also makes its left recursive call. So we went right, left, left, and got all the way over to this null right here. We made a recursive call with null, node.left is null. This doesn't do anything, it just returns. And then this node is going to pick up execution after the left recursive call, then make its right recursive call. So node.write is also null. And we put that on the stack and get this null check. This recursive call with null. And I want to take a timeout right here. We're going to take a breather. I'll ramble for a bit and watch for questions if there are any questions on this, because this right here is the crux of it. This is the most complicated that this trace gets, and after this part it's mostly returning and printing things to the screen, but this right here is there's a lot going on, and if you fully understand what's going on right here, you're going to be in really good shape going into the midterm. And in 2 days, goodness, the midterm's in 2 days already. You're gonna be in good shape if you get all this. So we have 4 stack frames on the stack. The main stack frame, which made a recursive call to the root, which is OX350, which made a recursive call to its left, handled all that left subtree stuff, made a recursive call to the right. So this stack frame, this traversal with OX350 is waiting right here. It's this arrow right here. Oh, sorry. I'm like, wait, that my color coding isn't matching then. It's because I'm wrong. It's this arrow right here. The lightest gray arrow is the first recursive call. It's waiting for its right recursive call to end. So it's remembering that once it gets back to the top of the stack, the next thing it's going to do is print itself to the screen and then pop itself off the stack. It made its right recursive call, so we have this recursive call with OX480. It's waiting for its left recursive call to end. It's made its left recursive call, and it's waiting for this to end so it can make its right recursive call, which will be null, and then it'll be able to print itself to the screen pretty quickly after that. And then we have this stack frame with OX936, this node right here, which is waiting for its right recursive call to end. And then once it gets to the top of the stack again, it's going to print itself to a screen and return. And then we have this stack frame, the current top of the stack, which is null, a call to null, the right child of this node. And it's null, so it's not going to do anything. It's just going to return. So each one of these stack frames needs to remember what to do once it gets control again. Two of them are waiting for its right recursive call. One's waiting for its left recursive call. But they have to remember where they're at in their execution, or else we're going to get all jumbled up. Everything's going to just be all messed up. And this is where the recursion helps us out. If you're writing this same code, a tree traversal with a loop, you have to keep track of all that information, all of that bookkeeping. You have to say, okay, are we visiting this node for the first time? Let's make the left recursive call. Second time, let's make the right recursive call. Third time, let's print to the screen, and then we're done with that node. You have to have some data structure, some way of managing all of that information yourself. With recursion, the stack is going to keep track of it all. So we're taking advantage of the stack and the fact that the program itself, each of these stack frames, is going to remember where it is in the execution. If you don't use recursion, you don't get that benefit. You don't have that anymore. There's something called a program pointer. Is that what it's called? I don't know. I haven't looked at the official name in a while. So off of memory, the program pointer, it's a 220 topic. You'll learn all about it there. That's going to remember this. So there's extra information in each stack frame, which does keep track of this information. We don't trace that in 116. I doubt they even have you trace it in 220, but they will explain it in more detail in 220. You have to remember where the program is in its execution. What line is it currently executing? That's remembered by each one of these stack frames. And after all that, no questions. So let's wrap this one up then. So this call to null just does nothing and returns. Returns back to this stack frame that was waiting for its right recursive call, so it prints to the screen and returns. Gives control back to this stack frame, which was making its left recursive call. It's going to make its right recursive call now. So we put that frame on the stack. We push that frame to the stack with null, which does nothing and returns. Then control goes back to this node, this stack frame, for the third time. It was waiting for its right recursive call. Now it's going to print to the screen and return. Back to the original call of the traversal method, which was waiting for its right recursive call to end. It's going to print to the screen, return. All the way back to the main stack frame, which has nothing left to do, is waiting for this method call to resolve, which had a lot of work, a lot of stack frames, a lot going on to get that one method call to resolve. But now that that method call stack frame has popped off the stack, we know that everything it needs to do is done. We gain control back to the main method, gain control, hit the closing brace, and the program ends. And it's the only memory diagram I'm going to do today. I'll also have I'll post the solutions to the sample quiz, so you have those also. But that's our tree memory diagram, which do get tedious. Like there's a certain amount I have to do to assess you on trees. These memory diagrams just get to be a bit. I gotta give you at least 4 nodes too. I won't go more excessive than that, but I gotta give you 4 nodes to really assess if you understand the order of traversals and things like that. So it just is a little tedious. But like I said, you're not gonna have these null checks, these null stack frames. So these will go away. If I see these null stack frames, especially since I gave it away in lecture so many times, if I see these null stack frames on your midterm, it doesn't bode well. And no question since 8:09, for over an hour. I hope y'all are still there. Binary search tree, BST. Let's roll right into it. So a BST, binary search tree, is a binary tree. The trees are binary because they can have up to 2 children. There are, like, you can write a tree class that has any number of child nodes. You could have a tree node class that has an array list of child nodes. Like, you can write that too. We're talking about the concept of a binary tree in lecture though. So a binary search tree is a binary tree that has these specific properties. It's going to take a comparator, and according to that comparator, whatever that comparator says, anything that comes before any node's value will go to its left, and anything that comes after that node's value will go to the right. And that needs to be true for every single node in the tree. If those properties hold for every node in the tree, you got yourself a binary search tree. So and for this one, I'm using the standard less than comparator. So for my lecture example, I'm going to use the less than comparator for integers. So we're going to get the typical increasing sorted order for integers, just because it's cleaner to say that, like, and I'll say less than and greater than throughout the lecture, just because that's cleaner than saying comes before in the sorted order according to the comparator, comes after in the sorted order according to the comparator. I'm not going to say that every time just because I don't have that much breath, but that will apply for all BST. Everything we talk about with BST will be based on any comparator. For your homework, it's going to be song title comparator and song Bayesian average comparator. But for lecture, I want to keep lecture simpler so we can focus on BSTs instead of getting bogged down with comparators. I'll just assume the comparator that's increasing, which would use the less than operator as its comparator in its compare method. So for lecture from here on, I'm going to say everything to the left is less than, everything to the right is greater than. It's just so much easier to say. So for the root, everything to the left is less than, and that isn't just the immediate left node, it's everything over here. Everything in the left subtree needs to be less than this node's value, which negative 3, 2, and 4, all less than 5. Everything to the right needs to be greater than. 7, 8, and 14 are all greater than 5. And this has to be true for every node in the tree. So this node 2, we go to the left, we find negative 3, less than. Go to the right, we find 4, that's greater than. 8, we find 7 to the left, that's less than. 14 to the right, that's greater than. So we're all good. This property holds for every single node in the tree. So this is a BST, which is the same exact tree from the previous set of slides. which was no mistake. I gave you a binary search tree to begin with. You just didn't know it was a BST yet. And then the only extra thing we need to talk about is how do we handle duplicates. When I get to the code, first of all, for the quiz, I'm not going to give you duplicates. If I gave you a BST on the quiz, there wouldn't be duplicates. On the homework, I don't test with duplicates. I'll never give you 2 songs with the same title or 2 songs with the same exact Bayesian average rating. And as long as you also don't test those situations in your tests, we don't have to worry about duplicate values. So my answer in 116 is we're just not going to worry about it. We're not going to worry about duplicate values because we got enough to worry about. Let's not worry about duplicate values. You don't test them. I don't test them. I won't put them on a quiz. Let's just not worry about them. But we do have to have, when we do write the code for a BST, we have to handle them in some way. My code is going to break ties to the right. So if I see a duplicate value, I'm going to shove it over to the right. And it will actually still work as a BST. When you implement a BST, you have to decide for your specific use case how you should handle duplicates. If you need the duplicates to be in there, you either always break ties to the left or always break ties to the right. Your duplicates always go left or always go right. As long as you're consistent, it's not going to break anything. The code's going to work exactly the way it should. Or just don't allow duplicates. Sometimes you don't allow duplicates. It's actually pretty common to say, if this is a duplicate, we're just not putting it in the tree. Whenever you try to add something to the tree, if you try to add a duplicate, not allowed. There are quite a few key value store implementations that are based on trees, and that's part of why you can't have duplicate keys in a key value store. Is if it's based on a tree, it's going to be based on a BST, and it's a self-balancing BST specifically, and it's not going to allow the duplicate key in its insert method. Or actually it will, it'll just replace the old value. It'll assume that you want to update the value at that key. It's not the best example because a lot of them are built on hash maps. Java makes that painfully obvious because it's called hash map. But some of them are based on trees, and they'll just not allow duplicates. So there are cases where we want to not allow duplicates at all. Pretty common case. So whatever your use case is out there in the future, in 116, we're just going to tactfully avoid duplicates. So don't write tests with duplicates. That'd be a good way to get incorrect on a correct, your tests are bad, fail the correct solution. That's what I'm trying to say. Your test failed the correct solution. If you have 2 songs with the same exact Bayesian average rating, and Bayesian average rating is your comparator that you gave that test case, very quick way to have some strange behavior. Because I never defined in the homework document how to handle duplicates. I'm pretty sure, hopefully I do, explicitly say don't test with duplicates. If not, I'm saying it right now. Okay, so that's a binary search tree. So let's build this class. That's what we want to do today, is write the code that's gonna do exactly this. Be a BST. So with a BST, it's very similar to our linked list of doubles in our song class when it took ratings. Similar to those, but the tree version of it, we're going to have an instance variable that is the root of a binary tree inside our BST class. And we also need a comparator. So we can sort based on any comparator that we're given. So we're going to take that comparator in the constructor of the BST and store that as an instance variable so we can call this comparator just like we did with our insertion sort class. We're going to have that comparator handy. So again, combining things that we've seen before, but in new and creative ways. The BST, by the way, when we're done with the BST class, you can just use the BST class straight up. Like you can take the BST class from the examples repo, copy it and paste it into your code, and in your playlist class, you can say new BST with this comparator from the playlist constructor. You're completely allowed to do that. The homework is not about implementing a BST. It's about traversing binary trees. That's what I'm asking you to do. That's what I'm assessing you on. Traversing a binary tree and constructing a linked list with an in-order traversal. That's what I want you to get out of the assignment. We're not going to build a BST. I'd like you to build a BST, but I can't lecture on BST without building it for you. And then, what am I asking you to do? Just copy lecture? Like, I'm just going to straight up tell you to copy lecture. So this is the BST class part of it. And what we want to do is figure out how to insert values into this BST and how to traverse the BST and find a specific value. These are the two things that we want to build today in lecture. So how do we insert a value into the BST and how do we find a value in this BST? And the key thing that'll come up in both of these methods is when we're inserting into a BST, we need to maintain the property of a BST. So everything to the left of a node has to be less than, everything to the right greater than, according to comparators, of course, assuming the less than comparator for ints. So we need to maintain that property. So we need to find a place to insert the new value that's going to keep that property, hold that property true. Maintain that property's truthfulness. I don't know. I didn't find the right words for that sentence. Hopefully you know what I mean. Those properties have to hold after the insertion. And if this method is the only way that we can add values to the tree, root is initially null to indicate an empty tree, just like empty linked lists, just like we represent an empty linked list. If the insert is the only way we can add values to the BST, which will be the case, and the insert method maintains that property, then the property will always hold for this BST. Probably. We can never be 100% on that. We can never be 100%. Mostly, actually, yeah, no, we can never be 100%. But it should. It's programming, so, I mean, strange bugs are always going to occur. The bug here would be, say I insert a song, but I also hang on to a reference to that song, and then I start calling that song setter methods, and change the values of the song's instance variables after I gave this BST a reference to my song. Like, that'd be a quick way to break things. But if you're a responsible programmer not doing silly things like that, then the BST property is always going to hold. And if A is a primitive type like integer, then, or any, I'm going too long on this tangent, but any immutable type like strings, then the property will always hold. But once it's a mutable type like song, which it will be in the homework, and you start messing with those song objects on the heap, you're going to destroy your BST. Don't mess with things on the heap. This is the general lesson there. And then the other thing is find. When we call the find method, we're going to assume that property does hold. We're going to assume that this is a proper BST and take advantage of that property to be able to find things. So insert is maintaining the property. Find is taking advantage of that property existing. And that's what we want to build this lecture. Let's build these two methods and see how to do this. So we're going to create a BST using an int increasing comparator, which we didn't build last lecture. We built int decreasing. So I want to use our comparator in the same way that we did before, but build the default comparator that uses the less than operator to compare two integers. This is going to give us our typical increasing order for integers. If you asked, ask someone in grade school to sort numbers, the standard order that you would think somebody would sort numbers in counting order. Less than operator is going to give us that as our comparator. We're going to insert a whole bunch of things into this thing. We're going to find some things. And then we're going to do an in-order traversal. Actually, I'm not going to trace through this code anyway. I'll just show you the end results. But that's what we want to do. So let's start with insert. Here's the code for insert. There it is. We're done. Insert. So let's go through this. How we're going to insert. And when you were writing recursive methods, we saw this a little bit with linked lists, but when we're writing recursive methods, we usually want some helper methods that are going to have the parameters that we want. Insert, the public-facing method, only takes the value that you want to insert, which is the way it should be. If I'm calling an insert method on some data structure or an add method, I just want to give you the thing that I want to insert. I don't want to have to tell you anything else. Like, just insert this thing into the tree, please. That's all I want. And the first thing this method will do is check for null. When we have these data structures where null is part of the structure, part of the way we build these data structures, we got to constantly check for null before we ever use the dot operator on a node. We have to check if that node's null. We just set root to null right here. Root can certainly be null. It's going to be null the first time insert is called. 100% of the time, it's going to be null. So we better have a null check before we start using the dot operator on this thing. Right here would be the first one. This would be our null pointer exception if we didn't have this null check right here. So before we can use the dot operator on this node, we sure as hell better check if it's null. So if the root is null, that means we have an empty tree. If we have an empty tree, well, I know where any value, I don't even have to look at the value that we're inserting. I know where it's going to go. It's the root. It's the first node I've ever seen. It's going to be the root of the tree. It's the very first value. So set the root equal to a new binary tree node, and we're done. If the tree already exists, then we're going to set up our recursion. We're going to have our helper method because I don't just want to know the value that I'm inserting. If I recursively call insert, it's not going to help me. I'm not going to be able to progress as I go down the recursion. I want to also know which node I'm currently considering for insertion. So if I know the node and the value I want to insert, that's all the information that I need, and then I can start making recursive calls on different nodes, different child nodes, as I go down the recursion to traverse this tree and find a home for this value that I'm trying to insert. So I want a second argument, or a second parameter, which is going to be the node I'm currently visiting, which starts at the root. So if the root's not null, start at the root, forward the value. Value is just going to keep being forwarded to each recursive call, and start the recursion. So the recursion is going to say, okay, I got this node. It's initially the root, but we can be at any point in the recursion. And we want to know where this value should go in this tree. So we're going to use our comparator. We're going to compare the value that we want to insert to the node's value, and we can do the opposite check. We could compare this in the opposite order. The difference is going to be the way we break ties. I said I'm breaking ties to the right, so I'm going to check, does the value I'm trying to insert go strictly before the value at this node? That's what I'm asking my comparator. The comparator returns true if the first argument goes strictly before the second one, and false otherwise. So false if this node's value comes after the value I'm inserting, or it's a tie. So I'm saying, does the value I'm trying to insert strictly come before this node's value in the full sorted order according to this comparator? That's the question being asked here. If the answer is yes, I'm going to the left, because the value that I want to insert goes to the left of this node's value. It has to, in order for this to be a BST. So I'm thinking left, and then now that I'm thinking left, I have to ask myself a question. Well, is the left node null? When I look to the left, do I see anything there? If I don't, I just found a home for this value. If I look left, I see nothing. I'm going to set that left to a new node with the value to insert. And I'm getting rid of that, finally getting rid of the dot left, dot value, dot right, getting rid of that stuff and using getters and setters like we should be. So set left to a new binary tree node with the value that we're inserting because we found a home. If we look left and we see something, we don't see a null, we're going to move over to that node through another recursive call. So we're going to make a recursive call on the left child, go over to that node and say, hey, well, there's a node there, so we haven't found a home for this value yet, but we're going to go over to the left and ask my left child, and they're going to figure it out. So we make a recursive call moving on to the left child until we, and then keep traversing the tree until we find a home for this value, which is a place where we find null. We're going to replace a null. If it's right, same thing, but over to the right. So if this comparator call is not exactly true, if it's false, that means either the value goes to the right or it's a tie, and I'm going to break ties to the right. This is how I'm breaking ties to the right. If toInsert is equal to this node's value, it's going to get shoved over to the right. So I'm breaking ties arbitrarily. As long as I'm consistent and I'm always going to the right, that's fine. But for what it's worth, I'm breaking ties to the right. I could break ties to the left. I could not allow ties. That's just the choice that I made for the lecture example, is breaking ties to the right. Same thing to the right. If I'm thinking right and I'm looking right and I see null, I found a home for this value. If not, make a recursive call and go over to the right child and consider that node as for finding a new home for this value. Visually, it's going to look like this. So say this is my binary search tree and I want to insert the value 7. I'm going to ask for each node, I'm going to start at the root node, and I'm going to ask, does the value that I'm trying to insert come strictly before this value? So is 7 less than 5 in our less than comparator case? Is 7 less than 5? That's false. So we're going to make a recursive call on the right child and ask the same question. Start the process over. So at this node, we're going to say, does the value I'm trying to insert come strictly before this node according to your comparator, which is less than in this case? We get true, 7 less than 8 in this case. So we're thinking left, we're looking left, we find null, there's nothing over to the left, so we found a home for 7. And the way this method is written, it's always going to preserve the property of a BST, because if the value is greater than, we go right. If it's less than, we go left. That's exactly the property of a BST. So we're exactly saying, let's maintain the property of a BST as we're searching for a home for this value. I think I only have one visually. So let's do another one. Let's just talk through another one. Then all the recursive calls on the stack are going to end. This one returns, and we return void, so there's no return value. So say we want to insert 4. Let's do a duplicate example. We're going to say, is 4 less than 5 true? Is 4 less than 2 false? Is 4 less than 4 false? So we have a tie, but our comparator is going to return false. It's strictly less than, because ties have to return false with our comparator. So we're going to look right, we're going to see null, and insert 4 right here. If we have, say, -2, we would say -2 less than 5 true, -2 less than 2 true, -2 less than -3 false. So we're thinking right, and we would insert it right here. We find null to the right. Let's do 15. Let's do one more. 15. They're quick enough. 15. Is 15 less than 5 false? Or 15 less than 5 false, so we go right. 15 less than 8 false, so we go right. 15 less than 14 false, so we go right. And we look right, we don't see anything, so we found a home for 15 right here. No matter what values we choose, we are always going to maintain the property of this BST. Let's do, actually 6 comes up a bit, because 6 is kind of a sneaky case. 6 less than 5 false, 6 less than 8 true, 6 less than 7 true, and then to the left of 7, this is where 6 would go, which does maintain the property of a BST. If we look to the right subtree of 5, everything's still greater than, and the left subtree of 8, everything's still less than. Left subtree of 7, everything's still less than. The property still holds for every single node after inserting 6. Even if we insert 6 a second time, it would go to the right of that 6 that we added. The property still holds for every single node. No question. I hope this is all making sense. I do get nervous when chat's frozen. As long as from everything I can tell, the stream's still working. Okay. So let's do find. So with find, we're on the other side of things. Instead of maintaining the property, we're going to assume that the property holds. We assume, oh, thank you, Foxykins. We're going to assume that the property holds and take advantage of that property to be able to find nodes efficiently. And efficiently is the key word. We're not really worried about efficiency in CSE116, but it really is the reason to use binary trees. So I will talk about efficiency a little bit at the end of this lecture, just because how else would we use a tree? I haven't really talked about the motivation of why we would even use these things yet, because oh, nice. Thank you, Matthew. That's good to know. I was getting nervous there with over an hour with no chat. I'm like, are they even there? It's good to know there's somebody out there. I'm not just talking to my computer like a crazy person. So we're going to take advantage of the property, and it is efficiency. That is the reason why anyone would use a BST ever. But I'm going to go through the find method first here. We're going to get our two methods, and then I'll start talking about efficiency, because that's the why. That was the why with linked lists as well. I don't know if I made that one super clear, though. When I talked about stacks and queues, we talked about big O notation a little bit. And the fact that a linked list can change size is very important. Your arrays can't change size. You have to have something like an array list that pretends it can change size by creating brand new arrays every once in a while, which is expensive. And if you want to add a value at index 0, you have to copy everything and push everything down the array list. That's very expensive, very slow operations. So if those are your use cases, then a linked list is going to be way more efficient than an array or even an array list. So talking about data structures, a common complaint, suggestion, I don't know, is I'm just going to use an array list for everything. A common approach, attitude, I guess. I'm going to use an array list for everything. Like anything you're doing with these data structures, I can do with an array list, which is a fair point. And they can be a lot easier to work with. You don't have to learn a whole bunch of data structures. But if you have a lot of data, things are going to start getting slow. Your code's going to be horrible. People are going to be waiting multiple seconds for your web page to load. It's going to be frustrating. And that's the reason why we learn data structures. And when you get to CSE 250, I'm kind of advertising CSE 250 here. When you get to CSE 250, that theming will be front and center of what's the most efficient way to work with these large quantities of data. That's a lot of runtime analysis in that course to figure out what the most efficient data structure is for the certain use cases. Because you can use an array list for everything. No one's going to stop you from doing that except your clients and bosses and everything, your customers. And if you have, I'll give a slightly hot take, like if you have less than 1,000 values in your data structure, just use an array list for everything. Like, who cares? It's when you start getting up in the tens of thousands, hundreds of thousands, millions of elements, that's when your choice of data structure really matters. That's where it's extremely important to get the right data structure for the job. But a lot of that's 250 talk. But that is, I realize I haven't given motivation for the linked lists properly. And BST, or binary trees, actually, yeah, just BSTs, not even binary trees. I will give some of that motivation here. But that's the why we're learning these data structures. Graphs will be a little bit different because graphs is representing data that is structurally different. So that'll be fun. But let's implement find. Enough of that. Find, if the root's empty, And this find is just going to return a Boolean. I decided not to return a reference to the node of this tree. We easily could. Instead of false, we can just, instead of true, we can return node. We could do that. For whatever reason, I decided not to do it. I already made my point with linked list that that's something we sometimes want to do. So I did not do it here. So if the root is null, we're returning false. If the tree is empty, we're not finding anything here. We're not finding the value. So we're going to go to our find helper. We're going to set up the same helper structure. We're going to have the node that we're currently visiting and for that value that we're trying to find. And we're not going to cheat this time. We have a type A, which can be anything. And when we did a find method in a linked list, we used dot equals, which we now know we're inheriting from the... We never overrode that. Did I get rid of the example where we override equals? But equals we do get from the object class. So every object in Java does have an equals method that we can use to be able to compare the two values. By default, on your objects, it's going dot equals, it's going to compare by reference. So it'll say, do these two references refer to the same object? I know I explained this, but I don't think we ever overrode the equals method. And we won't. Like, I'll never ask you to do that on a homework. I won't put it on a quiz. But kind of regret not having a lecture example just to show you what that's all about. I probably got rid of it because it's kind of a pain. It takes an object and you have to do type checking. It's kind of a pain, so maybe I don't regret it. But we can override the equals method. We're not going to, though, because we have a comparator. We're going to use this comparator to figure out if these two values are equal according to the comparator, which will sometimes be different than actual equality. So let's see what that means. So we're going to ask kind of the same question. Should we look left or right for this value? So we're going to use our comparator. Does the value we're looking for come before, strictly before this node's value? If the answer is yes to that, we know we should be thinking left. We've just eliminated the entire right subtree. If this value comes before, the value we're looking for comes before this node's value, whatever node we're currently looking at, then everything to the right of this node cannot possibly be the value we're looking for, because this value is less than, with our less than comparator, the node that we're considering. So it could not have possibly gone over to the right. That's not what insert would have done. Insert would have went to the left. So we're thinking left for sure. We're going to look left if we find null. For this one, I don't want to make recursive calls where node is null. So this is kind of the other style as well, where I'm not making recursive calls with null. I'm making null checks before my recursive calls. So if I look left and I find null, well, I didn't find what I'm looking for. If left is not null, I still have a chance of finding this value. I'm going to look left by making a recursive call, moving over to the left node, start over at the top of the method, but with node being the left child of the node that I just considered, and start the same process. And here's where things get a little bit different than insert. And here's where we see the full power of our comparator. I'm going to call our comparator again, but I'm going to switch the order of the arguments. I'm going to say, does this node's value come strictly before the value I'm looking for? That would mean that to find the value that I'm looking for comes strictly after this node's value, which means I'm thinking right. I have to go over to the right. If I have any chance of finding this value, it's going to be to the right. It cannot possibly be on the left subtree, because that's not what the insert method would have done, and that's not the definition of a BST. The definition of a BST says, if this is true, you can't be thinking left at all. You need to be thinking right. So we're going to look right, and if we don't find anything, then, well, we're out of luck. We're not going to find this value. If we look right and we do find something, there's still hope. We're going to go over to the right with a new recursive call, where node is the right child, and start over at the top again and do our checks at the right child. But here's the thing. If both of these are false, these values have to be the same according to this comparator. Because we don't directly have an equality check. The way our comparator returns a Boolean, it breaks ties by saying false. So if it returns true, that means the first argument comes strictly before the second argument, and false otherwise. So if this one comes after, or it's a tie, it's going to return false in both cases. But if I swap the arguments, if I say, hey, does toFind come before this node's value? And the comparator says, no. Returns false. And I swap the arguments. I'm like, well, does this node's value come before the value I'm looking for? And it says no again? If it says false both times, well, then I know these values are equal, according to the comparator. So that's a way that we can use this comparator that returns a Boolean, which seemingly has less information than the positive, negative, and zero style of comparator. Seemingly has less power than that, but it actually has just as much power. We just got to call the method twice with the arguments reversed. If it returns false both times, they're equivalent according to the comparator. Now, this is different than actual equality. That's a big reason why we don't want to use dot equals anywhere in here. This is different than actual equality because no matter what comparator we're given, we want to know if it's equal according to that comparator. And I say equal according to the comparator. By that I mean their sorted order does not matter. In a fully sorted value, if those two values are swapped, it'll still be fully sorted according to the comparator. The most blatant example of this that I've been beating you over the head with on the homeworks is ignoring case. So if I have two strings that are the same but they're different capitalizations of each other, the comparator that ignores case is going to return false and say these are equal according to the comparator, but they're not actual equivalent strings. If you hit them with dot equals, it's going to return false because they're not the same string, but they're the same string in the eyes of that comparator. Like the comparator doesn't care about the casing, the capitalization differences, so they're equivalent according to the comparator. Same with Bayesian average rating. If two songs have the same Bayesian average rating, it doesn't mean they're the same song. It just means they have the same Bayesian average rating. In which case we can return true. We found the value we're looking for, and then return true all the way up the recursion. Visually, it looks like this. We want to find the value 4. So the first thing we're going to do is say, hey, root, does the value I'm looking for come before your value? Is 4 less than 5 true? We're thinking left. We go to the left and we say, is 4 less than 2? That returns false. So we know we're not looking to the left. We eliminated the whole left subtree. Oh, I want to emphasize that point here too. Once 4 is less than 5, everything to the right has to be greater than 5 using the less than comparator. Everything to the right has to be greater than or equal to 5 in our case. So if 4 is less than 5, by transitivity, 4 is also less than anything over here, anything in the right subtree. And if it's less than everything, strictly less than, everything in the right subtree cannot possibly be equal to anything in the left subtree. So we don't have to, or the right subtree. So we don't have to look at the right subtree at all. We just eliminated this entire search space and we go to the left. Now with the left, we're doing the same thing. Is 4 less than 2? That's false. So we've eliminated the entire left subtree, but we still have a burning question. We want to know if this node has the value we're looking for. So we're going to ask the comparator again with the arguments switched. Does this node's value come before the value I'm looking for? Is 2 less than 4? That's going to return true. So we know that this node's value comes strictly before the value we're looking for. So we got to think to the right. So we head over to the right. And we're going to ask, is 4 less than 4? Is the value I'm looking for less than the value of this node? It returns false. So we know we've eliminated the entire left subtree, which is just null in this case. And then we swap the arguments. It's going to be the same comparison. Is the node's value less than the value I'm looking for, and we get false again. Since strictly less than returned false both times, now I know that this is the value I'm looking for. At the very least, it's equivalent according to the comparator. In this case, they're actually equivalent. They're actually the same numeric int. So we're going to return true. We're going to say we found what we're looking for right here because the comparator returned false no matter what order I gave the arguments. So we're going to return true up the recursion. So true, true. And let's give an example of I'll just leave this one on screen. Let's give it an example of not finding a value. Let's try to find the value 6. So we say, is 6 less than 5? That's false. So we eliminate the entire left subtree. Is 5 less than 6 is true, so we know to go to the right. So we go to the right. Is 6 less than 8? That's true, so we know we have to go to the left. Is 6 less than 7? That's true, so we know we have to go to the left. But when we look left, we find null, so we know that we cannot find 6. Because if 6 were in this tree, it would be right here. There's nothing there. 6 is not in this tree. Return false all the way up the recursion. Because there's no other place that you can put 6 in this entire tree that's going to maintain the property of a BST. So if we didn't find 6 right here, 6 ain't there. 6 is not in this tree anywhere. But the important part is how much we didn't do. We didn't check any of these nodes. We didn't check this node. We checked 3 nodes to be able to find if 6 is in this tree. Only 3 of the 7 nodes did we check to find out if 6 is in this tree. Same with 4. We only checked 3 of the 7 nodes. We eliminated all these with 1 check. And we eliminated this one with 1 check. And in the last check, we found what we were looking for. And very important point, I only have 1 slide on this. It's just like, I don't really have anything to say about it, but an in-order traversal of a BST will visit the node's values in order. So this is where we get use out of an in-order traversal. We go left recursive call, left recursive call, left recursive call, visit this node, right recursive call, visit this node, right recursive call, left recursive call, visit this node, etc. And then 7, 8, 14. We're exactly going to get sorted order. And this exactly follows the property of a BST. If we're doing an in-order traversal, we visit the entire left subtree, then the node's value, then the entire right subtree, which is exactly what a BST is. Everything to the left is less than, then visit the node, then everything to the right is greater than or greater than equal in our implementation. So we're exactly following the structure of a BST. We will visit every single node in sorted order, which is very important for task 5, which I've already spoiled multiple times, that you want to use an in-order traversal because you have a BST and you want to visit the nodes in order. In short, this is how search engines work. Search engines are a lot more complicated. I don't even know the full extent of how search engines works. A lot of AI and different things that go into it. This is how decision trees work, though. If you have like a simple AI, like this is how at least in the original Halo, I don't know if they're still doing this, how their AI decision trees would work. How to decide if an AI character is going to attack the player, run away, hide from a grenade. There's a whole bunch of Boolean checks in a tree that decide how that AI is going to behave. So each leaf node is a specific behavior, and it's going to ask a series of questions to figure out how to navigate the tree to get to an actual decision. Like, is the player within eyesight, yes or no? Is there a grenade nearby, etc., to find out how it's going to work. So decision trees do work like this, but search engines, they're a whole nother beast. They're pretty intense. There's a reason Google took over the whole internet. As soon as they came out with a search engine that worked well, because before Google, every search engine was pretty trashy. It is a bad time to be on the internet. But once Google came out with a solid algorithm, and everything just snowballed for them from there. But it's fairly complex. Okay, so everything in today's example was balanced. The binary tree was balanced, meaning that each node had the same number of descendants in its left and right subtrees. Everything was balanced. It was nice and symmetrical all the way down the tree. If a BST is balanced, which is a huge if, then we get a lot of efficiency properties out of our BSTs. So if the BST is balanced, the height of the tree, which is the longest path from the root to any null, so the length of the longest branch that from root to leaf, is log of n. So we have log n height. If it's exactly perfectly balanced, it'll be log n, which means insert and find take O of log n time. So each of those algorithms would visit a node in constant time. Each recursive call was constant time. And by the way, this runtime analysis, this will be huge in CSE250. I won't assess you on this stuff. So this, for the time being, is a nice to know kind of thing, or a preview of CSE250. But it's also the motivation of why we just talked about trees for 2 hours. So I want to make sure I get some motivation of why did we just do that? That sucked. Why are we going through this? Efficiency is the answer, and this is my explanation of it. So insert and find, it's constant time for each recursive call, and there are most log n recursive calls. Each time we made a recursive call, we were going to the left or right subchild, or left or right child. So we're going down the tree one layer every time we make a recursive call, and then doing constant time at each layer. So it's log n time for insert and find, which does give us a new sorting algorithm. Create a BST with your comparator, add all of your elements. You're adding n elements, and each insert takes log n time. You got yourself an n log n method to insert all the values, and then do an in-order traversal on it, and that's going to give you all the values in sorted order, which takes O of n time to do the traversal. So we have an n log n sorting algorithm. We have another one you saw very briefly, merge sort in 115. Here's another n log n sorting algorithm. We saw insertion sort earlier this semester. That's an n squared runtime sorting algorithm, which is horribly slow, horribly inefficient. You would never actually use that sorting method in practice. You would use an n log n sorting algorithm. And here's another one. For what it's worth, we got one. Kind of. If the BST is balanced. And the big payoff here is that we can maintain a sorted order in log n time. This is something arrays and linked lists cannot do. So if a value changes, if you have dynamic data, and I always think of a leaderboard, if I have a leaderboard with millions of players in my game, and I'm keeping track of their high scores in order, a global leaderboard for all these players, and their scores are constantly updating, constantly changing on me. If a new player comes in and they take the top spot, and I got that at index 0 in my array, well, now I have to move everybody else down one spot in this array, and I might have to create a whole new array if I have to resize, if that triggers a resize. So I got very slow insertion, especially when I have changes at the top of the leaderboard with an array. I'm going to get O of n operations there. Linked list, you can insert and change the size of a linked list extremely efficiently. That new player who takes the top spot, super easy. I can prepend in O of 1 time with a linked list, so even faster than a tree. But if I have to make changes towards the end or end of the list, I have to traverse the entire list. O of n jumps across memory to just get to the end of the list to be able to insert that node in constant time. And you might say, well, let's do the same thing we did with a queue and store a reference to the end and the beginning, and then we can make it a doubly linked list so we can traverse in both directions. Okay, but now we need to change the exact middle of the list. Okay, store reference to the middle of the list. Okay, now at the 1/4 and 3/4 spot. Like, it's not going to end. Like, there's always going to be some bad spots unless you store n references, and at that point you're turning your linked list into an array, and you don't get your efficiency. So array and linked list both O of n to insert or change a value in the list, where changing a value is can be seen as a deletion and insertion. But our linked list is, or our tree is log n. So inserting a new value, if we want to remove a value and then insert a value, it's going to be log n. We haven't talked about deletion, and I won't. But if we can do both those in log n, we can maintain the sorted order of dynamic data very efficiently with a tree. So this is one really strong advantage of a tree. If you just have to sort once and then that's your sorted order and the data is never going to change, arrays and linked lists are just fine. But if the data is changing, BST is going to be your hero. It's going to be your savior here. And just how strong is log of n? So we're saying log of n, log n, log n. But you've known this from math. You know log n. Log is a very slow growing function. But let's get a grasp on just exactly what log n means. So with our tree, we have a tree of size 7, and we had to visit 3 nodes in order to find what we're looking for or insert what we're looking for. Our worst case is 3. That's the height of our tree, is 3. And that's log of 7. Our logs in computer science are always base 2. Here it's because it's a binary tree. Our logs are going to be base 2. So we have the log of 8 minus 1. I mean, we lose out on one single node. But if you think of this as a tree of size 8, it's going to be 2 to the n minus 1, or 2 to the h minus 1 here. But if you think of this as a tree of size 8, 8 log 2 is going to be 3. The height of the tree is log n here. So we had to check log 8 of nodes, which is 3, to be able to get what we're looking for. So log of 7 is basically 3. It's a little less than 3 because it's a minus 1. So we have height 3. Log of 7 is roughly 3. Pretty good. I mean, less than half of the nodes, right? Log's pretty powerful, right? Less than half. Cool. What happens if the node has the tree has 1,000,000 nodes? How does this scale? If I have 1,000,000 nodes in my BST, what's the height going to be? Or in other words, what's log base 2 of 1,000,000? If I have 1,000,000 nodes in my BST, how long is my find going to take? How long is my insert going to take? These log n operations. How many nodes do I have to check? How many recursive calls do I have to put on the stack to get from the root all the way down to a leaf in a binary search tree of 1,000,000 nodes if the BST is balanced? You only have to check 20 nodes to get from the root to a leaf in a binary tree of 1,000,000 nodes. Log base 2 of 1,000,000 is a little less than 20. If I have 1,000,000,000 nodes, it's about 30. Trillion nodes, it's about 40. For every 3 zeros you add on to your base 10 number, log base 2 of that is about 10 extra. It's actually slightly less than 10 extra. So 1,000,000,000,000 nodes, the height of that tree is going to be 40. 1,000,000,000,000 values. If you want to find a specific one out of 1,000,000,000,000 in your balanced BST, even if the value you're looking for is not even among those 1,000,000,000,000 values, you're only checking 40 nodes. 40 values. You could do that by hand. If you have a BST with 1,000,000,000,000 nodes, by hand, you can check if a specific value is in that tree. That's how powerful logs are. They're extremely powerful, extremely efficient when we're talking about log runtimes. I mean, they're basically constants. Like if I coded this algorithm and had it run, you always have to check 5 nodes. Like 5 versus 20, sure, it's a factor of 4. In certain cases, you're gonna care, but when we're talking about versus a million, logs are powerful. This is ridiculously powerful stuff. This is how, if you've ever played those 20 question games, you think of something and the game asks you 20 yes or no questions, and then it gets to the end and it's like, well, I know what you're thinking of. It's this. It's computer. Like looking at my computer. Can't come up with examples on the fly. That's how it can do that. It can store a million different solutions, a million different things that you could be thinking of, and then ask you 20 yes or no questions and get to one of those 1 million things. That's how that game can seemingly come up with anything that you're thinking of. And that game, to be fair, it is a little more complicated than a straight up decision tree like this, or a straight binary search tree like this, but only because the games have to account for users who give wrong answers. So it can correct from you giving it wrong answers as well. So it can't be strictly just a BST like this. So it has to have a little more complexity. But it could just be a BST if everybody always gave the right answers. Sometimes I don't know the answers to those questions. It has to account for that. But all of that is if the tree is balanced. But what if the tree is not balanced? I was very careful to avoid any of this in lecture. But what if I gave an increasing, so the less than comparator, and inserted the values in sorted order? I'm going to insert -3. The tree is empty, so it has to be the root. I'm going to insert 2. Is 2 less than -3? False, so we go to the right. Insert 4. Is 4 less than -3? False. 4 less than -2? False. Go to the right. And so on with all of these values till we get to 14. 14 less than -3, less than 2, less than false, 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 false. And it goes all the way to the right. Which means we effectively have a linked list. Like, at this point, we have a linked list. We don't get any of the benefit of using a tree. We have O of n operations here. Finding a value is, worst case, going to traverse every single element. If this is 1 million elements, it's just a linked list of size 1 million. We're going to check every single one. This is bad. This is very horribly inefficient, the way we coded BSTs today. So we don't actually get the benefits of BSTs with this implementation. We are understanding how trees work. That's the goal here. Understanding what a binary tree is, understanding what a BST is, and then in 250 we'll fix this issue. So here's my last advertisement for 250. Is 250 is going to answer our big questions of how do we make use of these? How do we insert? We want to both insert and remove nodes. We didn't even talk about removing a node, but how do we insert and remove nodes in log n time while maintaining sorted order and keep the tree balanced? How do we even do that? 250 is going to show you how to do that. And the short answer is it's going to correct the tree. You're going to create what's called self-balancing BSTs through red-black trees and AVL trees. And what they're going to do is detect imbalances and then fix themselves. So the way this would work is, I believe once you insert the 4, it would rotate this tree, turn 2 into the root node, turn -3 into its left child, and 4 into its right child. And then as it gets imbalanced again, it'll do another rotation and keep fixing the tree as it becomes imbalanced. So it'll self-balance as nodes are being inserted, as values are being inserted. And then the duplicates, that'll always be a question when you're working with trees like this, BSTs. 250 is going to show you all of that cool stuff. Okay, and and that takes us to the third part, binary tree examples. I don't have slides on this because this is one case where I do get to go to the code in this lecture. How do I want to do this? Probably stash, pull. tree sum is what I want to build, but I'm not going to have time to do the whole thing. So let's keep this class and the tests. I'll explain that, and then tree sum, well, you can see the whole thing there. Maybe we do have time to do more than that. The algorithm is pretty simple. Let's write one test. I think that should be fine. We saw that. Okay. So I have this class thingamabob I created in lecture. I always ask the class, like, what should we create a tree of? What should be the things that we put in there? And they never have a good answer, so I always come up with the stupidest thing that I can. Thingamabob was what I came up with last time. So this is, I just need some class that has a couple values, because this is a stand-in for the song class. This would have 3 strings and a linked list of ratings. This would be your song class. I just want to give an example of a tree. That's the main purpose here. Give an example of a tree that stores references to objects, of custom objects. Because in lecture, I mostly just stick with ints in increasing order, which doesn't, helps explain the concepts, but it leaves a pretty big gap between what we see in lecture and what you're asked to do on the homework when you have a BST of songs with custom comparators. So I want to bridge that gap a little bit. So I just need something with a few values and the custom objects. I have the getters and setters, a constructor to initialize those 2 values. Nothing fancy here, nothing too much going on. We have a custom class with 2 instance variables. That's a double and a string. And what I want to do is create trees of this type and write a method that's going to return the sum of all of these numbers of that tree. So tree sum is going to take a tree, a reference to a binary tree node, which is presumed to be the root of the tree, and return the sum of all of these numbers, all of the numbers of those objects. So we have to call a getter to get the value of that number and then return it. So that's what we want to do. Actually, I might do another method here because this method's pretty straightforward. I might do a second one here. And then I want to write tests. So let's ignore the tests that we have. And I want to show how to write a test for this tree sum method. So we're going to write tree sum. And I always code out of order, just part of just how I code. So I know I'm going to call the method. The method's going to return an int. So I'll say this is actual. I'm going to have an int expected, which I don't know what it's going to be yet. And then I'm going to assert true. No, I'm going to assert equals. Assert equals, they're ints. Are they ints? No, they're doubles. I'm going to assert equals expected actual, and since they're doubles, I have to have some tolerance. Oops. Some tolerance, so I'm not checking for them for equality. I'm still seeing this on Piazza, by the way. You might be surprised to hear. We need some tolerance to be able to account for truncation errors. You have to have that whenever you're comparing doubles. Never ever use equal equal. Don't use assert equals. You even get a warning in IntelliJ. It says don't do that. because don't do that. And the new one I just saw for the first time, actually. It was a brand new one this semester. I haven't seen before. I saw somebody do this. They set their tolerance to 0. They said, no, check these for actual equality, which defeats the whole purpose. Defeats the purpose of everything, and really showed me that that student missed that point. They needed to go back and study that one. Okay, so let's create a tree. So binary tree node of thingamabob, root equals new binary tree node. And we have a lot of options here. I already showed you a few options. There's the way we did it in lecture today, where I did dot left, dot right, I did all this stuff. There's the way that I did it on the sample quiz, where I set values in the constructor, where instead of null, I would do like node 3 right in the constructor call. I'm going to do it a third way here. This is a way that I wouldn't put on a quiz for what it's worth, just because it's too much. It's too confusing to trace. But I'm going to do it here, just to show you another way of how to do things, because you might want to set your tests up this way on your task, on task 5, just because it saves typing and can be a little cleaner to do. So 3.5, let's give this some values. Description, it's a thing. About. So I'm going to give it this binary tree node constructor its value, its left, which sure I'll leave as null, and its right. But for its right, I'm going to create a new binary tree node right in line. So this can be a little tricky to read at first, but I mean, I've shown you all the other ways. I just want to show you a new way, so I think we can do a little trickier one. New thingamabob 8.9, and then give its left a new binary tree node, new thingamabob of negative, let's get some negative in here, negative 3.0 null. I think that's enough. We don't need this tree to be too big. And then we got to give the right child of, it can be confusing to line everything up. Oh, I forgot a description here. Another thing, and I forgot the description here. And my parentheses are imbalanced. Let's resolve that. Okay, binary tree node. This is one reason not to do this, is it's tough to line everything up. New binary tree node, thingamabob, left, right. New thingamabob, new binary tree node, new thingamabob, new binary tree node, another thing, left, right. Oh, what's this null doing here? No, because this binary tree doesn't have a right child. No, this shouldn't be here. And then we can format. The formatter is usually better about that. Oh, there we go. I just had my things on the wrong lines. So if you line these up and use the auto formatter, it can make it a little easier. This binary tree node has its value left and right, and when it's creating its right, if you balance the parentheses, this is the whole right node, which has its value, its whole left node, and then its right. So it's a lot going on in one big statement. But what I'm doing is creating a root with a a root with the value 3.5, a right child with 8.9, which has a left child of -3, and then nulls everywhere else. But we're only computing the sum, so all we have to do is sum up all the values of the tree to get our final expected. Should be 9.4. Then we can run our test, watch it fail. I always do like to see my tests fail. Because then I know it's actually testing something. If I know my method is incorrect, which it's always returning 0.0 right now, if my test fails, I know it's actually checking something. If you have intentionally wrong code and your test passes, you probably missed an assert. You probably don't have any asserts. Gotta have your asserts. Okay, and we have a whole bunch of other tests as well. To test this thing. There is something else I want to say here. So I do like to group my test cases. Like I'll have one test method that has a whole bunch of input and output pairs, and then it runs them all in a loop. I do like doing that, but for this specific one, when it's so complex to build the trees, I find this easier to build a new tree in a separate method every single time. So I'm creating more methods to set up my test cases, and then one test case per method. I just find it easier for this specific setup. Especially if you're naming your variables for each tree. If you do them all in one method, then you're doing test tree 1, test tree 2, and you're having all those issues. It's hard to avoid that unless you do a whole bunch of complex one-liners like this and then insert them all in a hash map. It just gets... I just find for this case it's easier to create a separate method for every test case. I don't get enough gain from running a bunch of test cases in a loop to offset how much it simplifies things by putting them in separate methods. I'm never going to have a cut and paste error where I meant to have test tree 3, but I still had test tree 2 in one spot. Like, I'm never going to have that issue here. Okay. So now that we have tests for this method, let's actually write the method. And as long as we're using recursion, this shouldn't be too hard. For the homework, when you're returning a linked list, it gets quite a bit harder. But let's take a stab at this. Double result equals 0.0. So let's have an accumulator. We're going to initialize our result, and this is what we're going to return. The tree could be null. Do I have a test case for that? Yeah, the tree can be null. And if this were a homework, I would say if the tree is empty, return 0.0 would be what I'd write for that one. So if the tree is null, I have to have that checked. If tree equals null. If tree does not equal null, I'm going to do something. So if the tree is null, I have to return 0.0. And I like setting up my methods in a way where that's just automatic. Any edge cases, if you can code them in a way where it's not really an edge case anymore, it tends to make the code a bit cleaner. So I'm going to say double result equals 0. If the tree is null, we just skip over everything else we're going to write and return 0.0. And the edge case just automatically handled. But if the tree is not null, then we want to make recursive calls to tree sum. So we're going to say, well, find me the sum of all of the values in the left subtree add that to all of the values in the right subtree, and those could be null. Those left and right could be null, but if the left subtree is null, if the left child is null, it's going to return 0. So it's not going to affect my sum calculations at all. And then at some point, I have to do result plus equals tree dot get value dot get the number. And this is the line that's actually going to do all the work and sum up all the values throughout the tree. And that's it. We can run our tests. The power of recursion makes this one fairly straightforward to write. And what I want to show here, let's go to the test that we just wrote and get some debugger action. It's hard to get debugger action in the summer, just because things go way too fast. There's not enough room to really get everything. But we got 5 minutes here. We're going to get some frickin' debugger action in here. So I can see that tree that I created. I have root, which is a reference to a binary tree node. Actually, I want this to be a bit bigger. Which is a reference to a binary tree node with a value which has 3.5 in this string. Its left is null. Its right is a binary tree node with the value 8.9. Its left is a tree node with the value -3. And everything else is null throughout this whole tree. So we have the root, right, and left is the whole tree that we've built. When we go into this method, I'm going to use the step into button. That's going to advance one line of code and go into any stack frame that's called. So I call tree sum, initialize result to 0. If the tree is not null, that's true. So we're going to make the left recursive call. So right now, this is a reference to the root of our tree. If we look at our what would be the main stack frame, but our test stack frame, the root is 1109. And 1109, that's the node that we have right now. Its left is null. So we're going to get a new frame on the stack. Oh. Yeah, okay, that worked. We're going to get a new frame on the stack where tree is null. So this is where we're doing our null check. Result equals 0. Null check false. Skip all the code and just return 0. So we're back into our first recursive call, our first call to tree sum. It was waiting for its left recursive call to end. That just ended. It returned 0.0, so we add that to result. Nothing really changes. Then it's going to make the right recursive call. So this stack frame right here, and it gives the line number in the debugger. It says, I'm waiting on line 19, or 9, I can't even read numbers. Line 17. And once line 17 is done, that's where I'm going to pick up execution. In our other stack frame, we're on line 28. It's going to tell us, I'm on line 28 right now. Once I get control again, I'm going to pick up execution right there. So now we're going to make the right recursive call. And what I almost oopsed here is whenever the debugger does this, it's asking you, it's saying, hey, there's 2 method calls here. Which one do you want me to step into? And it'll, if you just click again, it'll choose for you. But I like manually choosing. I'm going to click on tree sum. I don't need to debug a getter. My getter's working fine. That's going to put a new frame on the stack, and it gets that right child of the root. So it gets the reference 1113. So from the perspective of this stack frame, this node is the root of the tree. This node right here with the value 8.9 and a left child with -3. This effectively is the root for this recursive call. This recursive call, its job is to return what the answer would be if this node were the root node. It's going to make its left recursive call. So it's putting a new call on the stack, and we can see each one of these 3 recursive calls are waiting on different lines of code. They're all waiting at different places for their execution. Well, this one isn't even waiting. It's just going to execute. It's going to make its left recursive call with null, its right recursive call with null, and then add its value. I'm going to use this step over button because I don't want to go into the getter methods. And it's going to get that -3 and add that to result and return -3 back to this stack frame that was waiting for its left recursive call. So it made its left recursive call, which said the entire subtree, the entire left subtree, sum up all of its values. That subtree only had -3, and we did in fact get -3 added to result. We're going to make the right recursive call, which is just null. I'm going to skip over it actually. Skip over this one and add this node's value 8.9 to the -3 to get 5.9, and what this, and return that. And that goes back to the original stack frame. What the original stack frame gets is its right recursive call, which said if the right subtree was the root, what would be the sum? If this right subtree were the entire tree, sum up all of the values in the right subtree, which is 8.9 and -3, and tell me what that result would be. Add that to result, and we get 5.9, and then we're going to add the root node's value to that, 3.5, get our final answer 9.4, and return that back to the test. We get actual 9.4, expected 9.4. Everything's looking good. And our assertion passes. And we're at 10:31. We went 1 minute over. But we got some debugger juiciness in there. So I'm happy. Okay. I'm going to take a break before the 11 o'clock. I'll see everyone for the midterm. I didn't talk midterm logistics in this lecture, did I? So for the midterm at 8 a.m. on Thursday, I'm going to send an email with the 4 links to the quizzes and the tracing tool. It'll look just like your sample. It'll be the same interface as the sample quizzes. Do your traces, click submit, and then we'll grade through the tracing tool. So watch for an email. I won't go live at 8 a.m. on Thursday. I'm going to send you an email, and then I'll go live at 9:30 to 10:30 to talk about file I/O. Reading files and parsing CSV files. Okay. Take care, everybody. If I don't see you in office hours, good luck on the midterm.